In this lecture, I want to talk about the detrital sedimentary rocks. So these are the ones that are made of detrital sediment, which is the broken pieces that are not dissolved in water, but instead will float in water. They can be very tiny, small enough that you can't see them without a microscope, but they're not actually dissolved. So to make detrital sediment into a rock, we have to have that sediment deposited somewhere. So it's transported by wind or water, and then it's deposited somewhere. And then in general, it's buried under more sediment, and that compacts it down. So the process of lithification is what we call it when we take a sediment and make a rock into it. Right? So we're changing loose or unconsolidated sediment into a rock. There are two important processes that are involved in lithification. So one is just compaction, where you're just putting pressure on the rock, not a rock yet, on the sediment, and that sort of aligns everything and begins to remove pore spaces. So air and water and space are pressed out. So that's by compaction. Then the second process that happens is cementation. We're literally gluing the pieces together. So this happens when little tiny crystals of different minerals end up being deposited between the grains. So here, this is done when groundwater circulates through the grains. So you can see there's a lot of pore space, a lot of space here between all the grains. Crystals deposit out and fill that space in, and that glues the pieces together. So just like with the igneous rocks, we need a set of characteristics that we can use to classify or name the sedimentary rocks. So with the igneous rocks, we use their composition in terms of what minerals they were made of, and we also use their texture, whether it was phaneritic or aphanitic or glassy. For the detrital sedimentary rocks, we also are going to look at texture and composition. Texture plays the largest role. Composition plays a secondary role. So texture includes the size of the pieces or the grains. We usually use the term grains. So we can have small grains or we can have large grains. Rounding is a second characteristic. In this case, we've got things with sharp edges or things that are nicely rounded. And then finally, sorting, which is just a way of looking at a sediment and saying, are all the pieces very similar to one another? So we're going to talk about each of those in more detail. And this creates a visual texture. Again, a visual texture. We're not talking about how the rock feels to the touch. All rocks feel rough to the touch unless you've cut and polished them. So it's a visual texture that we see in the rock. One of the reasons that these characteristics are important is also because they tell us something about the history of the sediment. So remember, the sediment was created through weathering, and then it might have been transported a long way through wind or water before it was deposited to become a new rock. So we get some information about what happened to the sediment along the way from these characteristics. First, grain size can range. You can see that in this figure, we've actually got numbers, like how many millimeters the grain sizes are. What we're going to do instead is focus just on sort of tiny, medium, and large. So mud is what we call the tiny sizes of sediment. That includes silt, which is like a very tiny, fine sand, and clay, which you would actually need a microscope to see. You can't see the individual grains with your eye. Sand ranges anywhere smaller than a Rice Krispie treat a Rice Krispie that makes up the treats. So sand can actually range from coarse sand to medium sand to fine sand. So you have to remember that not all sand is going to be exactly like beach sand. Some of it will be a little coarser. And then gravel is basically anything larger than a Rice Krispie. We tend to think of gravel as sort of pebble size, but actually it can range from a Rice Krispie size, just a little bit larger than sand, all the way up to boulders. So grain size again gives us a little information about the history of the sediment, right? It tells us how far the sediment has been transported. When grains are broken off of a rock and then are transported by rivers and wind, they tend to bounce around against each other and the bedrock, and that decreases their size. They break into smaller pieces. Glaciers are an exception because glaciers freeze sediment into the glacier itself. So they freeze the sediment in place. So that means that the sediment does not bounce around, so they don't change the size because of that. So the next characteristic was rounding. This is also telling us something about transportation, because again, when the little pieces get knocked up against each other and the bedrock, they tend to break off all the sharp corners, and that's how they become rounded. Same issue here with glaciers. Since they're frozen in the ice, the pieces don't change shape. So rounding doesn't really have to do with the shape of the piece. So these are both rounded pieces, even though this one is kind of long and narrow. The important thing is that the sharp corners have been broken off. So you can see you start here or here with kind of sharp edges, and by the time you get all the way to here, those sharp edges are gone. So we can have angular pieces, subangular pieces, meaning that the sharp edges are beginning to get rounded off, sub-rounded, mostly rounded, and then very rounded, where you have basically really smooth the pebble. So sorting was the third characteristic we look at, and this is how similar the grains are to each other. Usually in terms of grain size is the primary thing, and somewhat in terms of rounding. So this image here is just using different shaped, different sized spheres or circles to show the effect of sorting. So we start out with something that's very poorly sorted because it has lots of different size circles in it. And slowly over time, the big circles end up getting smaller and smaller, and that's what would happen to the rocks. The big pieces get smaller and smaller. They get broken down into smaller pieces. And then eventually, when we have a well-sorted sediment, all of the pieces are approximately the same size. Rivers and wind, again, are quite efficient at this because the pieces get banged around a lot, so they change size. With glaciers, nothing happens to the sediment, so however it enters the glacier is the same way that the glacier eventually deposits it. One of the ways in which rivers and wind sort sediment is that heavier pieces tend to fall out when you end up with lower energy. So let's say you start out with a mountain stream. It's going down a steep slope and it has a lot of energy to the water because of the gravity pulling things down. So that kind of water can move fairly large pieces downstream. But when you get to the end of the mountain, the bottom of the mountain, and things begin to flatten out as you get into the mountain valleys and down into the foothills, the energy of the water decreases. And when that happens, the bigger pieces simply are deposited and don't move any further. What that means is that now it's just a subset of smaller pieces that are continuing to be transported. And that subset of smaller pieces then is better sorted because we don't have the bigger pieces anymore. So now the pieces are all more similar in size to each other. The same thing happens with wind. Wind is actually really good at sorting things when it picks the sediment up. A strong wind can pick up heavier sediment, but if you have a lighter wind, then it can only pick up pretty fine sediment. So only that fine sediment is going to be moved and deposited somewhere else. So that's another way in which sediment can be sorted, so that what is deposited is more similar within the sediment. They're all more similar to each other. This graphic just shows that change. We go from mountains, where sediment initially breaks off of rocks, and then that sediment is transported downstream toward a coastline. So at first, the sediment has lots of different minerals in it, lots of different shapes, and most of it is fairly angular, right? So we have angular here and unsorted. And then as we continue to go on, more and more of the minerals are going to be weathered away, right? So we're actually decreasing the diversity of the minerals as well. Things like feldspar, for instance, are not going to make it very far. So we end up with a less diverse sediment, so less minerals because of weathering, and specifically the chemical weathering. And also you can see that some of the sharp edges on the pieces have been worn off. So we've started to see some rounding going on here. And then finally, when we get down to the beach, all of this gray mineral, maybe that's the feldspar, has been weathered away. And the yellow minerals have been broken down so that all the pieces are more similar in size. So we're left with a very well-sorted sediment. All the pieces are similar in size. They're more similar in the type of mineral and in the rounding. So that's a natural process that happens as we move from the center of the continent towards the edges or the coastlines. And again, this could be our quartz sand beach, right? We have quartz, which is very resistant to weathering, and a lot of it ends up resisting the weathering and making it to the edge and end up creating that beach. So when we name the sedimentary rocks or classify them, grain size is the first characteristic we look for, and then rounding, sorting, and mineral composition come later. We're going to start with very fine grained sediment, so that's the first size category that we're going to do. And the rock names in this category include shale, siltstone, and mudstone. They're all very similar, and for instance, in your box of minerals, you will have one of those, but you could call it shale, siltstone, or mudstone. All of those names are referring to the same rock. The texture is very fine grained, right? We're talking about mud-sized grains, so you should not be able to see any individual pieces. The composition includes a lot of clays. Mud is basically made of clay, lots of different clays, along with some micas, little tiny pieces of quartz, etc. But the main dominant mineral will be the clays. So where was this sediment deposited? You need some place with very quiet water in order to have these very tiny pieces actually make it down through the water column and be deposited on the bottom. So you would never find this kind of sediment being deposited in those really fast-running mountain streams. This kind of sediment is going to be washed down. But once you get to, say, a place like the Kishwaukee or the Rock River, you have a much slower, less energetic water flow. And there are places there where mud can actually settle. You also would find mud sized particles settling in a lake bed. The bottoms of lakes are often very muddy. It's very quiet water. And of course, in a swamp or any kind of a marsh or anything like that, again, you have very quiet water, so you'll deposit mud there. So thousands of years later, that mud then gets lithified into the rock shale. Shale is a very soft rock. It really is lithified mostly through compaction. There's not a lot of cement between the grains, and that makes it fairly soft. So you can see in this photograph that it's fairly easy to break. It has these layered edges, partly because it's made of clays and micas, which are both sheet silicates. And then up here in this top photo, you can see it's not a great slope to do any rock climbing on or anything because it breaks under your feet. So you end up with a slope that has a lot of broken pieces on it. So the next size category is medium-sized grains. So these are sand-sized grains. So remember, things that are smaller than Rice Krispies but bigger than the mud. The two rock names that we're going to learn in this category are quartz sandstone and arkose. There are two additional sandstones that we're not going to focus on, but you may read about. A lithic sandstone. Lithic just means rock, so this is a sandstone made of multiple different rock pieces that are sand-sized. And then a greywacke, which is kind of a funny name, but it is a sedimentary rock that forms near volcanoes where most of the sediment is actually weathered basalt. So we're not going to focus on these two, and the reason we're picking these two is because they're the most different from each other. And that makes the characteristics a little easier to remember. So first one, quartz sandstone. The texture is going to be medium grained because it's made of sand. And the most important textural characteristic to remember to help you identify it is that it is made of a well-sorted sediment. So when we look at the sample here in the photo, what we see is a very uniform look because of how well sorted the sediment is. All the grains are the same size, all the grains are rounded to the same amount. They've been cemented together, so it's it's a pretty strong rock, definitely stronger than the shale. You get color differences, but those are due to the cement. So the color can vary a lot. You can have white sandstones, white quartz sandstones, orange quartz sandstones, red quartz sandstones. Hematite cement will give you a red sandstone. Calcite or silica cement will give you a white one. There are some little clay minerals that will act as a cement and give you the yellow or orange. That's a color that you see a lot down at Starved Rock Park. Those bluffs are all sandstone, quartz sandstone. And those colors, the orange and the sort of lighter tan colors, come from being cemented together with tiny crystals of clay minerals that are kind of yellowish in color. So it's called a quartz sandstone because it is 90% quartz grains. So we have the texture, the size of the grain, the fact that it's sandstone as the primary reason we call it a quartz sandstone, right? This is how we categorize it using the grain size, medium grained. Then we have the sorting and the composition as the secondary characteristics for naming it. Where would this sediment be deposited? Well, this is what quartz sand beaches eventually become. So if you think about that with Starved Rock, those are some very thick layers of quartz sandstone. So at some point in history, this area had a huge amount of beach sand basically accumulating on it. And that later became the rock, the Peterson sandstone down there. These are some more photos of the quartz sandstone. This one is a little bit magnified so that you can kind of see individual grains. Notice these changes in color again. This is going to be from the cement that has cemented this together. And those changes come because remember, the cement comes from groundwater flowing through the rock or the sediment. And as that groundwater moves through, it deposits different minerals depending on what it was carrying. So the second medium-grained sandstone that we are going to do is Arcos. So you can call it Arcos or you can call it an Arcos sandstone. Both are appropriate. The biggest textural difference between this and the quartz sandstone is that this rock has sediment that is poorly sorted. And you can see that in the pictures. This does not have that same nice uniform look to it that the quartz sandstone had. Poorly sorted means we have some grains that are larger than sand-sized, and it also means that we have some grains that are angular and some that are rounded. So you can certainly see some large grains here, right, that have been incorporated into this sandstone, and that's where that poor sorting comes from. Another important thing for an Arcos sandstone is its composition. It has to have at least 25% potassium feldspar. So this grain that I circled here, and this grain here, and this grain, those are pieces of potassium feldspar that we can see in the rock. The rest of it is made of other rock fragments, quartz grains, micas, clays, everything else that you could find in a sedimentary rock. This 25% feldspar does give us some information about this rock. Feldspar is weathered away pretty quickly by hydrolysis. So hydrolysis requires water. So what we are going to find is that the sediment that creates this rock was deposited in a relatively dry environment, not too much water or rain. So not a lot of it got weathered away. Also, the fact that it has these larger grains and some angular grains tells us that the sediment wasn't transported very far and probably was deposited very quickly after it broke off of whatever source rock it came from. Some pictures of Arcos. We've got these pieces of potassium feldspar in these, but you can also just see that it's much less uniform in look. This is comparing the two again, so we have the very uniform look for the quartz sandstone, and this one is the poorly sorted sediment. Again, well sorted tells us that the sediment traveled a long distance. So the quartz sandstone likely formed from a beach, and the sediment on the beach was mostly quartz, and that's because that sediment had traveled far enough from its source rock where it broke off that most of the other minerals had been weathered away, and all of the quartz grains had been broken down into about the same size, and their corners, their sharp corners, had been rounded off. The Arcos tells us that the sediment that makes it up did not travel far. It had to have been deposited very quickly after it was broken off of the source rock. That's the only way you would maintain sharp edges and such a variety of different sizes, so not having a very uniform look. And again, the fact that it has potassium feldspar tells us that it must have actually been deposited somewhere where there was not a lot of water around. It didn't travel in a stream or a river for a long period of time, because if it had, the feldspar would be gone. Finally, we come to the last size, which is the largest size, so coarse-grained. Remember, that actually means anything larger than a Rice Krispie, though, so while this picture has very large pebbles in it, they don't have to be this large. And in small samples, things like you have in your sample boxes, we're not going to have pieces with huge grains in them because even the grains wouldn't fit in the sample boxes. Conglomerate is the name of this one, so gravel-sized grains, and what's specific about a conglomerate is that it has rounded clasts or grains. When the pieces get big enough like this, we often call them clasts. So you can see how the edges here of these clasts have been rounded off. They're not sharp, right? There's also a fine-grained matrix that cements the bigger clasts together. So it can have a whole bunch of different sizes in it, anything up from mud to sand to even pebbles. Because the composition can vary so much, and because these larger pieces are actually rocks in themselves, right? This piece here is a rock, and it could have multiple different kinds of minerals in it. It hasn't broken down into individual minerals. So we use the word lithic fragments, the phrase lithic fragments, to talk about the composition. We don't talk about specific minerals, we just say these are rocks that are made of broken rocks. Where would you find a sediment like this? Well, one place is if you just drive due east and go to Lake Michigan. The beaches along Lake Michigan and Illinois tend to have a lot of gravel-sized pieces. So those pieces end up rounded, you can see that here, not because they've been traveling in one direction, but because of this wave action. They get basically moved around back and forth by the waves, and that does the rounding. So a gravel beach is the place where you would find this sediment being deposited. So when you come across something like a conglomerate, you can assume that it formed someplace where you had large sediment, but you had some sort of motion with water that was moving it around and allowing those pieces to be rounded. The second type of rock that's made from the gravel-sized grains or the coarse-grained rock is a breccia. And a breccia is coarse-grained, but it has angular clasts instead of rounded. So in this case, we can see very sharp corners on the pieces here that have been enclosed in the finer-grained matrix. Composition, again, is going to be lithic fragments because we are talking about, again, pieces of a rock. We don't know what minerals are in those rocks. So where would we find this kind of a sediment being deposited? Well, landslides is one. In a landslide, you basically have sediment that falls down a hill. Usually a tall hill, but still it just falls down and gets deposited right there. Talus slopes, which we mentioned earlier in the chapter 6 lecture, are a place where you have rock break off in mountains and just fall down and accumulate here at the base of the mountain. That's a talus slope. That's another place where you will end up with very angular pieces, right? They're not traveling very far, so the angular sides, little points and things are not being rounded off. You also can end up with very big pieces because, again, they haven't been traveling, so they haven't broken down into smaller pieces. So just to compare the breccia and the conglomerate, right, we've got rounded pieces over here, rounded clasts. So nice rounded, again, they don't have to be spherical, they just have to have their rounded corners, right, rounded off. And then over here, we've got the angular clasts. So we can see sharp corners here, sharp corners here, and down here in this one as well, too. So they're very similar. They're both large pieces that are basically kind of glued together with a finer grained matrix, but we distinguish conglomerate from breccia by the shape of the pieces that make them up, the larger pieces. So this is just a picture of sediment, different kinds of sediment. And I just want to emphasize in here that when you name sedimentary rocks, remember that you're not looking at the rock itself. You're naming it by the sediment. So when you're talking about something being rounded, you're talking about a grain that's in a rock, not the rock itself. And sedimentary rocks can have mineral crystals in them, like we have in this picture, right? We have little quartz grains here, something like a pyroxene that's dark here. This looks like maybe an olivine. It's nice and green. They can also have shells, like we have up here, so we can see actual shell material in here. These pieces are broken pieces of shells. You can usually tell because of the little tiny holes that they have in them. They're a little more spongy than a mineral. And then again, just a mixture of different things. Shell material that's been broken, shells that are whole, pieces of coral, and pieces of quartz. Lots of different kinds of sediment. And then finally, this figure is from your book, and I want to modify it slightly because they actually lump sandstones all into one category here, and we are not doing that. We are looking at two different sandstones. So the picture here is the quartz sandstone. The Arcos is the one that is poorly sorted.